Hello everyone. Welcome to the ILTA Physics online class. Today, we're going to study a classical field of traditional physics, dynamics. Dynamics is the branch of physics that deals with forces, the pushes or pulls that make objects move. More specifically, we'll study and analyze quantitatively how these forces affect the motion of objects. In this lecture, we'll first take a brief look at the relationship between the motion of an object and the forces acting on it. Then we'll finish by introducing several types of forces that we'll learn about later, such as weight, spring force, tension force, and friction, all of which we often experience in our daily lives. All right, let's step into the new world of dynamics. Let's begin by defining what we mean by a force in physics. In everyday language, we use the word force in many different ways. But in dynamics, we define force as something that causes an object to move. In more scientific terms, a force is an influence that causes a change in an object's velocity. To explain force properly in dynamics, we must define two objects first. A force is always described as an interaction between two objects: the agent, which exerts the force, and the object, which receives the force. For example, imagine a child sitting in a toy car being pushed by two friends. In that situation, the car is the object, and two friends are the agents applying the force. That's an important concept. In dynamics, force is always defined as a relationship between two objects. Also, a force is a vector quantity. It has both magnitude and direction. Intuitively, we can describe a force by saying how strong it is and which direction it acts in. Usually, forces act through pushing or pulling actions. If you push an object, it moves away from you. If you pull it, it moves toward you. That's consistent with our everyday experience. A force makes an object moves. For instance, in the figure showing someone pulling a spring, the person is the agent applying the force, and the spring being stretched is the object. We can categorize forces based on whether the agent and the object are in direct contact or not. Forces that act through physical contact, like pushing or pulling a box, are called contact forces. Forces that act without direct contact, like gravity or magnetic attraction, are called long-range forces. Finally, one important characteristic of forces in dynamics: as we said, a force always acts between two objects. That means the force appears as two equal but opposite forces acting on each object. This is the Newton's third law of motion. We'll explore that in detail next time. Now, let's see how we can represent forces. When several forces act on one object at the same time, for example, when multiple agents apply different forces, we can define the net force as the vector sum of all those forces acting on the object. Remember, it's not just a simple arithmetic sum of magnitudes, but a vector sum because each force has a direction. For example, imagine three students standing on an ice rink seen on the right. The student in the middle is the object, receiving the forces, and the two students on either side are agents applying forces. If one student pushes the middle one to the right, and another pushes upward at the same time, the middle student will move diagonally toward the northeast. That motion results from the vector sum of the two applied forces. We can express this relationship mathematically like this. But do we have to draw people every time to understand how forces work? Previously, when studying motion, we used motion diagrams, simple and visual representations instead of drawing entire cars or people. In the same way, in dynamics, we'll use a powerful tool called the free body diagram to represent the forces acting on an object visually. A free body diagram is a simple sketch showing all the forces acting on an object. For example, in the above skating situation, we represent the object as a single dot, and each force acting on it is drawn as an arrow. It is a vector. An important thing to remember is that the tail of each force vector should start at the object. even though it might feel more natural to draw the arrow toward the object. In a free body diagram, we always draw arrows starting from the object and pointing in the direction of the force. The direction of the arrow shows which way the force acts, and the length of the arrow represents the force's magnitude. Finally, we label each arrow appropriately. And that's it, your free body diagram is complete. From now on, throughout this chapter, we'll draw free body diagrams for every problem we solve. Don't worry, you get used to it soon. Now, let's briefly introduce the different types of forces we'll be studying in this unit. Let's start by talking about the force called weight. We often use this word in everyday language to talk about how heavy something is. But in dynamics, weight is actually a force. Weight is the force that Earth pulls on an object near its surface. In other words, it's the force Earth uses to pull things toward itself. We usually use the symbol W for weight, or sometimes we write F with a small subscript like FW or FG to show that it's the force of weight or gravity. Weight is a type of long-range force because it acts even when objects aren't touching directly, like between Earth and an object. Now, take a look at the picture on the right. Let's say there's an object sitting on a table. The Earth is pulling that object downward toward the ground. Since we are just starting to learn about forces, let's take a moment to figure out who's doing what here. The agent applying the force is Earth, and the object receiving the force is the item sitting on the table. And because this is a pulling force, the direction of the force is toward the Earth. That means weight always acts straight down toward the center of the Earth. And this is true even if the object is moving, the weight always points downward, no matter what. Now, in everyday life, when we talk about how heavy something is, we're usually just talking about the magnitude of the weight, how strong that downward force is. But this is different from mass, which is a property that belongs to the object itself. We'll go into more detail about that a bit later. Next, let's talk about the spring force. You've probably seen springs in everyday life. A spring tries to go back to its original shape when it gets compressed or stretched. So you can think of spring force as the force that tries to return the spring to its normal shape. As you can see in the diagram below, when a spring is compressed or stretched from its normal position, a force appears that acts in the direction that would bring it back to where it started. It might not feel familiar yet, but the red arrows in the picture show the force acting in each case. Now let me ask you, don't those arrows seem a little different from what you expected? In the top diagram, the spring is being compressed to the left from its normal position. So you might think, hey, I pushed it to the left, so shouldn't the force arrow also point to the left? Well, you do have to push it left to compress it. That's true. But this diagram shows what's happening after the spring is already compressed. It's showing the force the spring applies back on the object. In this case, the spring is the agent applying the force, and the object receiving the force is the little box attached to the spring. So the force points to the right, which is the direction the spring is trying to push the box back to. This is really important. When you're analyzing how objects move, you need to clearly identify who is applying the force and who is receiving it. That will help you understand the situation correctly. Spring force is a bit special because, unlike some other forces, it can either pull or push depending on the situation. Now, because it's called spring force, some people think it only happens in actual metal springs. But that's not true. Take a look at the picture on the right. If you bend a thin plastic ruler and then let go, it wobbles back and forth and tries to return to its original shape, right? The restoring force is also considered a type of spring force. So basically, any force that tries to bring something back to its original shape or its equilibrium position is a kind of spring force. You might have noticed the word equilibrium here. Don't worry, we'll go into more detail about what that means in the next section. Now let's move on to the tension force. We usually write this with a capital T, and it shows up when an object is hanging from a rope or a string. Let's look at the diagram on the right. Say you're holding up a heavy object using a rope in your hand. Let's try to figure out what forces are acting in that situation. I know it might still feel new, but don't worry, this gets easier with practice. First, the Earth is pulling the object downward with gravity. That's the weight, labeled W, and it acts downward. But the object isn't falling, right? That means there must be an upward force, and that's the tension force from the rope. If the object is just hanging there, not moving up or down, then the tension force and the weight are equal in magnitude but opposite in direction. So then, what about the T shown above the rope, near your hand? That's also a tension force, but it's acting between your hand and the rope. It's part of a different system. It's not directly about the object hanging below. I get that this can feel a little tricky at first, but don't worry, you'll get the hang of it with practice. Now, here's something important. Tension force always acts along the direction of the string or rope. In the diagram at the bottom, there's a person standing on a tightrope. Here, the tension forces act along both sides of the rope, pulling toward the ends. Also, tension force always pulls. It never pushes. I mean, just think about it. If you try to push something using a rope, it's not going to work, right? All right. We've only got a few more types of forces left to go. Let's join forces. Let's keep going. Next up is the normal force. We usually write it as N or sometimes Fn. It's not the most intuitive concept at first, but here's how we can think about it. The normal force is the force that a surface applies to push back against an object that's resting on it. For example, if you're sitting on a bed, the springs in the mattress compress, and as a result, the mattress pushes you upward. That upward push is what we call the normal force. And the normal force always acts perpendicular to the surface the object is resting on. In the picture on the right, there's an object sitting on a table. In this case, the normal force is the force the table pushes upward on the object. It means the agent is the table, and the object receiving the force is whatever is sitting on it. And again, the direction of this force is always at a right angle to the surface. Now, about the word normal. This doesn't mean regular or not weird. In this context, normal is a math term, and it means perpendicular. So even though the normal force might not feel intuitive at first, it's a really important concept that we'll use a lot when we study classical dynamics and motion. Now let's talk about friction. Yes, this is the same kind of friction you've heard about in everyday life. It's the force that resists motion between two surfaces that are in contact. More specifically, in dynamics, friction acts between an object and the surface it's resting on, and it always acts against the direction of motion. Or in other words, it tries to keep things from moving. Let's look at the picture below. There's a box on the floor, and you're trying to pull it to the right. Friction tries to stop that motion, so it acts to the left. Why does friction happen? Well, look at the zoomed-in part of the diagram. Even if a surface looks smooth, it's actually kind of bumpy on a microscopic level. Those little bumps get caught on each other, and that's what causes friction. The amount of friction depends on how strongly the object is being pressed into the surface, kind of like how hard the two surfaces are being pushed together. In the diagram on the right, if the object isn't pressing down very hard, there's a tiny gap between the object and the surface. But if the object is pushing down with more force, the surfaces get tighter together, and that creates more friction. Earlier, we said the normal force always acts perpendicular to the surface. Well, friction force is the opposite. It always acts parallel to the surface, and opposite to the direction the object is trying to move. Friction is super important when we analyze motion, and in dynamics we usually split it into two types: static friction when the object isn't moving, and kinetic friction when it is moving. We'll take a closer look at each of these types in upcoming lessons. Next, let's talk about drag. It's usually written with a capital D. This force appears when an object moves through a fluid like a gas or a liquid. Drag resists the motion of the object, just like how friction resists motion on a surface. Earlier, we said friction happens between a solid object and the surface it's on. Well, drag is the version of that for fluids like air or water. The most common example you've probably heard of is air resistance. Just like friction, drag always acts in the opposite direction of the object's motion. It tries to slow the object down. What's special about drag is that it gets stronger the faster the object moves. So in sports like bobsledding, where the speed is very high, drag becomes a big deal. Also, drag increases when the fluid is more dense. For example, drag is stronger in water than in air because water is denser than air. That's why Olympic swimmers wear those tight bodysuit swimsuits, like the one in the picture on the right. The goal is to reduce drag as much as possible. On the other hand, if an object is moving slowly, or if it's moving through something like air that isn't very dense, then the drag is pretty small. In those cases, we often ignore drag in physics problems to keep things simple. Next is thrust, along with electric and magnetic forces. Thrust is the force created when an engine, like on a rocket or airplane, pushes gas backward using explosions or high-pressure fuel. The force on the rocket goes in the opposite direction of the gas being expelled. We'll understand this much better later on when we learn about Newton's third law. Finally, let's briefly talk about electric and magnetic forces, which we'll study in more detail next semester. These forces happen when charged particles are inside electric fields created by charged metals or magnetic fields created by magnets. The particles feel a force because of the field they're in. We'll dive deeper into these topics later, but for now, just know they're part of the bigger picture of forces in physics. So today we explored the relationship between forces and motion, and we got an overview of the different types of forces we'll be working with in this course. Next time, we'll start to look at these forces and motions more quantitatively, using numbers, equations, and real-world problem solving. Great job today, everyone. See you next time.